What if we could predict which friends on your social network are most likely to influence you? What if we can use AI to discover a new drug by just analyzing some complex patterns in the molecules? This isn't science fiction, it is the power of graph neural networks. A graph is a combination of a set of objects called nodes and the relationships between them, edges. Think of it as your social friends group, where each person is a node and the relationship between the person, the friendships, become the edges. Or just as atoms are nodes and the chemical bonds are edges inside a molecule. On the other hand, neural networks are powerful tools which are used for finding patterns in data like images or text. The traditional neural networks like CNN for images, RNN for text are often used, but they struggle with the non-grid like data, and GNNs come into picture. They fill the crucial gap by learning from the connections between the nodes, not just their individual features. But how do GNNs actually do that? They do this via an iterative process called message passing. Think of it as a rumor spreading through a network. In each layer, node aggregates information from its immediate neighbors, updates its own state, and passes the new information on. This, in real time, is taken in three steps. Message. Each neighbor creates a message based on its features. Aggregate. The central node collects all the incoming messages and combines them into one single vector. Update. The node updates its own features vector by combining from its previous state with its new and aggregated information. On the right, you see a graph convolutional network proposed by Kipf and Welling in 2016. This is a foundational model which uses a simplified version of this process. To demonstrate this, I have implemented GNN using Geometric on the Cora dataset, which is a citation network. Our goal is to classify each paper into one of the seven academic fields. First, let's look at the raw data. As you can see, a TSNE plot of an unprocessed features shows the academic fields are completely scattered and mixed together. There is no clear pattern for the traditional model to learn from. Well, our GNN model consisting of two GCN layers taking 1433 input features and transforming them into 16-dimensional embedding, which is then used for classification. After training for over 200 epochs, the model's test accuracy increases to nearly 80%. Finally, let's visualize what the GNN has learned. To visualize this high-dimensional data, we use a technique called TSNE, again, which usually helps us creating two-dimensional maps of data showing how similar or different nodes are. And our plot suggests that the papers are now organized into tight, distinct clusters, visually proving that GNN has successfully learned to group the data by academic field by simply analyzing network of citations. But are GNNs really special? The power of GNN isn't just theoretical, they are actually transforming industries. They are useful in the social networks as recommender systems, provide us better user experience, and also useful in drug discovery because they can analyze intricate graph structure of molecules which cannot usually be done easily. They are now paving path in healthcare industry, booming it up. They're also becoming crucial in fraud detection, identifying complex patterns in financial networks to protect consumers and businesses. GNN research is also rapidly advancing by creating new models like graph attention networks, graph sage, and also geometric GNNs, which even go further by incorporating three-dimensional information, which is a major breakthrough for things like molecular design. To conclude, just look at this image. To the left, scattered and unorganized data, raw data, and on the right, after our GNN has trained, the nodes of same color are now tightly clustered. And this isn't magic. Looking ahead, as data becomes increasingly interconnected, the ability of GNNs to understand and leverage these relationships will only become more vital, promising breakthroughs in areas we haven't imagined yet, from personalized medicine to smart cities. Thank you.